Tonight, we're going to explore something that will fundamentally reshape how you understand the universe. We're going to journey into the space between the stars. Not the stars themselves, but the vast, unimaginable emptiness that separates them. Because here's what most people don't realize. When you look up at the night sky and see stars scattered across the darkness, what you're actually seeing is almost nothing. The stars are the exception. The emptiness between them is the rule. And that emptiness is so profound, so incomprehensibly vast, that it challenges everything we think we know about distance, time, and our place in the cosmos. By the end of this journey, you'll never look at the night sky the same way again. Before we dive in, if you enjoy these deep explorations of the cosmos, a quick like or subscribe would really help this channel grow. It's a small gesture that means a lot to me. But for now, get comfortable and settle in. Let's begin. Let's start with something you probably think you understand. Space. You know what space is, or at least you think you do. You've seen the pictures. Astronauts floating in orbit above the Earth, rockets launching toward the moon, rovers trundling across the rusty surface of Mars. You understand that space is up there, above the atmosphere, and that it's mostly empty. But here's the thing most people don't realize. When most people think about space, they think about the objects in it. The planets, the moons, the asteroids, the stars. They think about destinations. What they don't think about is what lies between those destinations. And what lies between them is almost everything. Interstellar space. That's the technical term for the region between stars. It's not just empty space in the casual sense, it's a specific environment with its own properties, its own characteristics, its own challenges. And it makes up the overwhelming majority of our galaxy. When you look at the Milky Way stretching across the night sky on a clear, dark night, you're not really looking at stars. You're looking at the tiny, infinitesimal fraction of the galaxy where matter is clumped together enough to shine. The rest, the vast majority, is the dark ocean of interstellar space. Think of it this way. Imagine you're looking at the Pacific Ocean from an airplane. You see scattered islands below. Some are large, some are small, but they're all separated by enormous expanses of water. From up high, the ocean dominates your view. The islands are the exceptions, the rare places where land has risen above the waves. That's what our galaxy is like. The stars are islands, bright, hot islands of nuclear fire where matter has concentrated enough to ignite fusion. But between those islands is an ocean, a vast, dark, almost incomprehensibly empty ocean that stretches for light years in every direction. When you see the Milky Way, that band of pale light crossing the heavens, you're seeing the glow of billions of stars, so distant that they blur together into a continuous river of light. But for every point of light you can see, for every star that shines in that band, there's an immense volume of darkness. The stars are the exception. The emptiness is the rule. And tonight, we're going to explore that emptiness. We're going to try to understand what it really means when we talk about the space between stars. Now, to understand interstellar distances, we need to talk about light years. You've heard this term before, probably many times. Scientists use it constantly when discussing anything beyond our solar system. But I want to make sure you truly understand what a light year means, because it's the key to grasping everything else we're going to discuss tonight. Light is fast. Incredibly, almost unimaginably fast. Light travels at about 186,000 miles per second. Not per hour, not per minute, per second. In the time it takes you to blink, light has traveled about 18,000. 600 miles. That's nearly 3/4 of the way around the Earth. In 1 full second, light can circle our entire planet about 7.5 times. It could travel from New York to Los Angeles and back more than 37 times. Light moves so fast that for most of human history, people assumed it was instantaneous. You turn on a lamp and the room is lit. There's no perceptible delay. The light just appears. But light isn't instantaneous. It has a speed. A very high speed, but a finite one nonetheless. And that speed has been measured with extraordinary precision. The exact value is 299,792.458 kilometers per second, but for our purposes, 186,000 miles per second is close enough. A light year is simply the distance that light travels in 1 year at this incredible speed. If you do the mathematics, multiplying the speed of light by the number of seconds in a year, you get approximately 5.88 trillion miles. Let me write that out so you can see it. 5,880 billion miles. That's a 5 followed by 12 zeros. It's a distance so large that it defies easy comprehension. There's nothing in human experience that prepares us for numbers like this. Our nearest stellar neighbor is Proxima Centauri, a small red dwarf star about 4.24 light years away. That means the light you see from Proxima Centauri tonight, if you could see it, which you can't because it's too dim for the naked eye, that light left the star over 4 years ago. It's been traveling through the darkness of interstellar space for more than 4 years, moving at 186,000 miles per second, and it's only just now reaching your eyes. Think about what that means. If something happened to Proxima Centauri right now, at this very moment, if it suddenly brightened or dimmed or exploded, we wouldn't know for over 4 years. The light-carrying news of that event would still be in transit, making its way across the vast gulf of interstellar space. We keep seeing the star as it was, not as it is, for years to come. This isn't just a theoretical curiosity. It's a fundamental limitation built into the fabric of the universe. Information cannot travel faster than light. When we look at distant stars, we're always looking into the past. But 4.24 light years is just a number. Let's try to make it real. Let's try to understand what this distance actually means in terms we can relate to. Imagine you could drive to Proxima Centauri, not in a spaceship, just in your car, cruising along at a steady 70 miles per hour. How long would the trip take? The answer is approximately 40 million years. 40 million years of continuous driving, never stopping for gas, never sleeping, never taking a bathroom break. Just driving hour after hour, day after day, year after year, millennium after millennium for 40 million years. Let me put that in perspective. 40 million years ago, the Earth looked very different. The continents were in different positions. The Himalayas were still rising. The ancestors of modern whales had only recently moved into the oceans. Horses were tiny, dog-sized creatures. The Mediterranean Sea didn't exist yet. You could have started your drive back then, when the world was almost unrecognizable, and you'd still have millions of years left to go. You'd drive through ice ages and warm periods, through the evolution of countless species, through everything that eventually led to the appearance of humans, and you'd still be driving. The distance is that immense. Let's try something faster. What about an airplane? A commercial jet cruises at about 550 miles per hour. At that speed, you could reach Proxima Centauri in approximately 5 million years. Still an incomprehensible span of time. 5 million years ago, our ancestors, hadn't yet developed into anything we'd recognize as human. The entire evolutionary journey from tree-dwelling apes to modern humans has taken less time than this flight would require. What about something genuinely fast? The fastest object humans have ever built is the Parker Solar Probe. This spacecraft, launched in 2018 to study the Sun, uses the Sun's gravity to accelerate to remarkable speeds. At its closest approach to the Sun, it reaches velocities of about 430,000 miles per hour. That's fast enough to travel from New York to Los Angeles in about 20 seconds. It's fast enough to circle the Earth in under 4 minutes. By any human standard, this is an almost incomprehensible speed. At this speed, how long would it take to reach Proxima Centauri? About 6,500 years. That's still longer than all of recorded human history. The first cities were being built about 6,000 years ago. Writing was just being invented. The pyramids of Egypt didn't exist yet. You could have launched the Parker Solar Probe when humans first started recording their thoughts in written form, and it would still be traveling today, with centuries still to go before arrival. Then there's Voyager 1, our most distant spacecraft. Launched in 1977, Voyager 1 is currently traveling at about 38,000 miles per hour relative to the Sun. It's been journeying outward for nearly 50 years and is now the most distant human-made object in existence. At its current speed, how long would it take Voyager to reach Proxima Centauri if it were headed in that direction? About 73,000 years. 73,000 years ago, modern humans were still in Africa, just beginning to spread across the world. Neanderthals still walked the earth. The last ice age hadn't even started yet. Everything that we think of as human civilization, all the cities and empires and technologies and discoveries, all of it has happened in a fraction of the time it would take Voyager to reach our nearest stellar neighbor. And here's the thing that really drives this home. Proxima Centauri is the closest star. It's our nearest neighbor. The stars you see in the night sky are mostly much farther away. Sirius, the brightest star in the night sky, is about 8.6 light years away, roughly twice the distance to Proxima Centauri. Vega is about 25 light years away. Polaris, the North Star, is about 430 light years distant. The stars of the Orion constellation range from 240 to over 2,000 light years away. The center of our galaxy is about 26,000 light years from here. These aren't just big numbers. They're distances so vast that they fundamentally change what travel and communication mean. At these scales, everything we think we understand about moving from one place to another breaks down completely. Let me try one more approach to help you visualize these distances. Scale models. Humans are good at understanding things we can see and touch. So let's shrink the universe down to something we can hold in our hands. Imagine the sun as a grain of sand. A small grain, about 1 millimeter across. At this scale, how far away would the Earth be? About 4 inches. You could hold the sun in one hand and the Earth in the other, separated by a few inches of empty space. At this scale, the Earth itself would be far too small to see. A microscopic speck smaller than any grain of dust you've ever noticed. Where would the outer planets be? Jupiter, the largest planet in our solar system, would be about 20 inches from the Sun. Saturn would be about 3 feet away. Uranus would be about 6 feet away. Neptune, the outermost major planet, would be about 10 feet from the Sun. And Pluto, The most famous of the dwarf planets would be about 13 feet away at its average distance. So our entire solar system, from the Sun out to Pluto, would fit in a decent-sized room. The Sun is a grain of sand. The planets are specks too small to see. And the whole system spans maybe 40 feet at most, if you include the more distant reaches of the Kuiper Belt. Now, at this same scale, where the Sun is a grain of sand, how far away would the nearest star be? 18 miles, not 18 inches, not 18 feet, 18 miles. You'd have a grain of sand here, representing our Sun and everything orbiting it. Then, you'd travel for 18 miles past neighborhoods and shopping centers and industrial parks, across an entire city and out the other side. And finally, you'd find another grain of sand representing Proxima Centauri. And in between, nothing. Just miles and miles of empty space. This is our stellar neighborhood. This is what it means when astronomers say Proxima Centauri is our closest neighbor. It's a grain of sand 18 miles away from our grain of sand, with absolutely nothing in between, and most stars are much farther away than Proxima Centauri. At this scale, where the Sun is a millimeter grain of sand, Sirius would be about 36 miles away. Vega would be about 106 miles away. The center of our galaxy would be about 110,000 miles away, nearly halfway to the Moon. The nearest large galaxy, Andromeda, would be about 10 million miles away, roughly 40 times the distance from Earth to the Moon. The emptiness is staggering. Stars are not scattered like glitter on a dark canvas. They're more like grains of sand scattered across a vast desert, separated by miles of nothingness. The universe is mostly empty space, and that emptiness is the defining feature of interstellar space. Let me tell you more about our stellar neighbors, because understanding them helps illustrate just how sparse this neighborhood really is. The closest star system to our Sun is Alpha Centauri, which is actually a triple star system. 3 stars gravitationally bound together, orbiting their common center of mass. Alpha Centauri A and Alpha Centauri B are the 2 main stars, forming a close binary pair that orbits each other every 79.9 years. Alpha Centauri A is remarkably similar to our Sun. It's a yellow main sequence star with about 1.1 times the Sun's mass. If you could somehow transport yourself to a planet orbiting Alpha Centauri A, you might look up and see a Sun very much like our own. Alpha Centauri B is slightly smaller and cooler, an orange dwarf star with about 90% of the Sun's mass. The third member of the system is Proxima Centauri, a tiny red dwarf star with only about 12% of the Sun's mass. Proxima orbits far from the main pair, taking over 500,000 years to complete one orbit. It's currently the closest of the 3 stars to our solar system, which is why it gets the name Proxima, meaning nearest. Proxima Centauri is so small and dim that despite being the closest star to us, you cannot see it without a telescope. It's a faint red ember, barely managing to sustain nuclear fusion in its core. The next nearest star is Barnard's star, a red dwarf about 6 light-years away. Barnard's star is famous among astronomers for having the highest proper motion of any known star. Proper motion is how fast a star appears to move across the sky relative to more distant background stars. Most stars appear essentially fixed over human timescales, but Barnard's star moves noticeably over decades. Even so, it would take about 180 years for Barnard's star to move across an angle equal to the width of the full moon. Stars are far away, and even the fastest moving ones seem almost stationary to us. Wolf 359 is about 7.9 light years away. Another red dwarf, dim and small. You might recognize the name if you're a fan of science fiction. It's been featured in various stories and shows, probably because it's close enough to be a plausible destination while still being impossibly far by current technology. Leylande 21,185 is about 8.3 light years distant, yet another red dwarf. In fact, red dwarfs dominate our stellar neighborhood. They're the most common type of star in the galaxy, making up about 70 to 75% of all stars. But they're so dim that none of them are visible to the naked eye, despite being the most numerous stars around. Sirius sits at about 8.6 light years away. Unlike the previous stars I mentioned, Sirius is bright. It's the brightest star in our night sky, a brilliant white beacon that's been known to humans since ancient times. But Sirius isn't bright because it's particularly close. It's bright because it's intrinsically luminous, putting out about 25 times more light than our Sun. Sirius is actually a binary system, with a white dwarf companion called Sirius B orbiting the main star. Within 10 light years of our Sun, there are fewer than 10 star systems. Within 20 light years, there are approximately 130 known star systems. Let me put that in perspective. A sphere of space, 20 light years in radius, contains a volume of about 33,500 cubic light years. 130 star systems in 33,500 cubic light years works out to an average of one star system per roughly 260 cubic light years. That's an enormous amount of empty space for every single star. If stars were evenly distributed, which they're not, but if they were, each star would have its own private bubble of emptiness about 6 light years across in every direction. Miles and miles of nothing between every grain of sand in our desert analogy. The universe is overwhelmingly empty. Stars are precious, rare concentrations of matter in a cosmos dominated by void. Now, let me tell you about a spacecraft that has actually ventured into this void. Voyager 1, humanity's most distant emissary. Voyager 1 launched on September 5th, 1977 from Cape Canaveral, Florida. It was one of 2 Voyager spacecraft, along with Voyager 2, designed to take advantage of a rare planetary alignment that occurs only once every 175 years. This alignment allowed the spacecraft to use the gravity of each planet to sling itself toward the next, visiting multiple worlds with a single mission. Voyager 1 flew past Jupiter in March 1979, sending back stunning images of the giant planet and its moons. It discovered active volcanoes on Io, the first volcanism ever observed beyond Earth. It revealed the complex structure of Jupiter's ring system and atmosphere. Then it swung past Saturn in November 1980, exploring the ringed planet and its fascinating moon, Titan. After Saturn, Voyager 1's primary mission was essentially complete, but the spacecraft was still functioning, still traveling outward, still capable of sending data back to Earth. So NASA kept listening, and Voyager kept going. For decades, Voyager 1 traveled through the outer reaches of our solar system, through a region where the sun's influence gradually weakens. You see, our sun doesn't just sit quietly in space. It constantly emits a stream of charged particles called the solar wind. This wind flows outward in all directions, creating a bubble around our solar system called the heliosphere. Inside this bubble, the environment is dominated by particles and magnetic fields from the sun. Outside, the environment is dominated by the interstellar medium, the gas and dust that fills the space between stars. The boundary between these two regions isn't sharp. It's a gradual transition zone. In 2004, Voyager 1 crossed a region called the termination shock, where the solar wind abruptly slows from supersonic to subsonic speeds. This happens because the solar wind is running into the interstellar medium and being forced to slow down. It was Voyager's first indication that it was approaching the edge of the sun's domain. After the termination shock comes the heliosheath, a turbulent region where the slowed solar wind swirls and churns as it interacts with the incoming interstellar medium. Voyager spent years crossing this region, sending back data about conditions that no spacecraft had ever experienced. Then, in August 2012, something remarkable happened. Voyager 1 crossed the heliopause, the outer boundary of the heliosphere. Beyond this point, the solar wind no longer dominates. The environment is controlled by the interstellar medium instead. Voyager 1 had entered interstellar space. This was a historic moment. For the first time in human history, an object built by human hands was traveling through the space between the stars. The data Voyager sends back is precious. It's our only direct measurement of what interstellar space is actually like. What has Voyager found? The interstellar medium is different from what Voyager had been traveling through. The density of particles is higher than in the solar wind, though still incomprehensibly sparse by any Earth standard. The magnetic field is oriented differently, no longer aligned with the sun's magnetic field, but following the larger patterns of our galactic neighborhood. Voyager detected an increase in cosmic rays, those high-energy particles that stream through the galaxy, because the heliosphere had been partially shielding it from them. But here's the sobering reality. Voyager 1 has been traveling for nearly 50 years. It's moving at about 38,000 miles per hour. It's currently about 15 billion miles from Earth, far beyond any planet, far beyond even the Kuiper Belt. And yet, it hasn't scratched the surface of interstellar space. At its current speed, Voyager would take about 73,000 years to reach Proxima Centauri if it were headed in that direction, which it's not. Voyager is traveling toward a point in the constellation Camelopardalis, the giraffe. In about 40,000 years, it will pass within about 1.6 light years of a star called Gliese 445. It won't come particularly close, it will just drift past in the cosmic night, a tiny artifact of a species that may or may not still exist by then. Voyager 1 carries a golden record, a phonograph recording attached to the side of the spacecraft. This record contains sounds and images from Earth, greetings in 55 languages, music from different cultures, from Bach to Chuck Berry to traditional songs from around the world, natural sounds, surf, wind, thunder, birds, whales, 116 images showing life on Earth, from mathematical definitions to human anatomy to landscapes and cities. The Golden Record was designed as a message to any extraterrestrial intelligence that might someday find Voyager. It's a bottle thrown into the cosmic ocean, a greeting from one small world to whoever or whatever might be out there. But here's the truth. Space is so empty, so inconceivably vast, that the chances of anything ever finding Voyager are essentially zero. The spacecraft will travel through interstellar space for billions of years, long after the sun has exhausted its fuel and expanded into a red giant, long after the Earth has been consumed or scorched lifeless. Voyager will drift through the darkness, silent and alone, and it will almost certainly never encounter anything, No star, no planet, no curious alien vessel, just the void. Forever. This isn't a sad fact. It's just a true one. And it illustrates better than any number or analogy just how empty interstellar space really is. You can throw a message into that ocean and it will drift for billions of years without reaching any shore. The distances and the emptiness are simply that immense. So what have we learned so far? We've learned that interstellar space is the region between stars, and that it makes up the overwhelming majority of our galaxy. The stars are islands. Interstellar space is the ocean that separates them, and that ocean is vast beyond human comprehension. We've learned that even our nearest stellar neighbor, Proxima Centauri, is over 4 light years away. That means even light, the fastest thing in the universe, takes more than 4 years to make the journey. Our fastest spacecraft would take tens of thousands of years. And Proxima Centauri is the closest star. Most stars are far, far more distant. We've learned that if you shrink the sun down to a grain of sand, the nearest star would be over 4 miles away. Miles of emptiness between grains of sand. This is the true scale of our stellar neighborhood. We've learned that within 20 light years of our sun, a volume of over 33,000 cubic light years, there are only about 130 star systems. Space is overwhelmingly, dominatingly empty. And we've learned that Voyager 1, after nearly 50 years of travel at speeds no human has ever experienced directly, has only just begun to explore interstellar space. It will drift for billions of years and probably never encounter anything. This is the first part of our journey. We've established how far the stars are. We've tried to build some intuition for distances that defy easy comprehension. But we haven't yet explored what fills this vast emptiness. Is interstellar space truly empty? What would you find if you could somehow travel through it? What challenges would face any spacecraft or traveler trying to cross it? The ocean between stellar islands is not quite as empty as it first appears. There's something out there in the darkness. Not much. Almost nothing really. But something. And understanding that something is the next step in our journey. The void awaits. Let's explore what fills it. We've established how far the stars are from one another. Light years of distance. Tens of thousands of years of travel time with our fastest spacecraft. Grains of sand separated by miles of nothing. But now we need to go deeper. Because interstellar space isn't just far. It's empty. Empty in a way that challenges human comprehension. Empty in a way that makes the word itself seem inadequate. When you say something is empty, what do you mean? An empty room still contains air, trillions upon trillions of molecules in every breath you take. An empty bottle still contains atmosphere, countless particles bouncing off the glass walls. Even the vacuum of space as we typically think of it, the space between Earth and the Moon, contains particles. Not many by Earth standards, but some. Solar wind streaming outward from the sun, occasional atoms drifting through, bits of dust. Interstellar space is different. Interstellar space is empty on a scale that defies our intuition, that breaks our normal understanding of what emptiness means. The voids between stars contain so little matter that calling them empty almost undersells it. They're not just empty, they're as close to nothing as the universe allows. And yet, they're not completely empty. There is something out there in the darkness between stars. Not much. Almost nothing, really. But something. This something has a name. Scientists call it the interstellar medium. And understanding the interstellar medium is essential to understanding what any traveler between the stars would actually encounter. So let's explore what fills the great emptiness. Let's find out what's really out there in the ocean between stellar islands. The interstellar medium is the material that exists in the space between stars. It's made primarily of gas, with a small admixture of dust. The gas is mostly hydrogen, the simplest and most abundant element in the universe, accounting for about 70% of the interstellar medium's mass. Helium makes up most of the rest, around 28%. The remaining 2% or so consists of heavier elements, what astronomers call metals, though this includes things like carbon, oxygen, and nitrogen that chemists wouldn't consider metallic at all. The dust component is much less abundant than the gas. For roughly every 100 billion hydrogen atoms in the interstellar medium, there's about one dust grain. These grains are tiny, typically smaller than a micrometer, made of various materials including silicates, carbon compounds, and in colder regions, water ice. But here's what's truly remarkable about the interstellar medium. Despite containing all this gas and dust, it's still almost unimaginably sparse. The average density of the interstellar medium is about 1 atom per cubic centimeter. One single atom floating alone in a cubic centimeter of space. Let me put that in perspective. The air you're breathing right now contains approximately 2.5 times 10 to the 19th power molecules per cubic centimeter. That's 25 quintillion molecules, 25 billion. Every cubic centimeter of the atmosphere around you is packed with this inconceivable number of particles, all bouncing off each other, creating the pressure you feel, carrying sound waves, supporting the flight of birds and aircraft. The interstellar medium, by comparison, has 1 atom per cubic centimeter on average. The ratio between these two numbers is about 25 sextillion to 1. The air around you is roughly 25 sextillion times denser than the average interstellar medium. This is a number so large that comparisons become meaningless. It's like comparing the mass of a single bacterium to the mass of the entire Earth. The scales are so different that they don't really compare at all. But the interstellar medium isn't uniform. It has structure. It varies from place to place, with denser regions and sparser regions, hotter zones and colder zones. Astronomers have identified several distinct phases of the interstellar medium, each with its own characteristics. Understanding these phases helps us appreciate just how empty most of interstellar space really is. The densest and coldest regions of interstellar space are called molecular clouds. These are vast structures where conditions are right for hydrogen atoms to pair up and form molecular hydrogen. They're called cold because temperatures in these clouds can drop as low as 10 Kelvin. That's about negative 441 degrees Fahrenheit or negative 263 degrees Celsius. Just 10 degrees above absolute zero, the coldest temperature theoretically possible. At these frigid temperatures, atoms move slowly. When they collide, they can stick together, forming molecules. This is where chemistry begins to happen in interstellar space, where atoms combine into more complex structures. Molecular clouds contain not just hydrogen molecules, but also carbon monoxide, water, ammonia, and even complex organic compounds. Over 150 different molecules have been detected in these clouds. Molecular clouds are also where stars are born. When a region of a molecular cloud becomes dense enough, gravity takes over. The material begins to collapse, falling inward under its own weight. As it collapses, it heats up. Eventually, the center becomes hot and dense enough for nuclear fusion to ignite, and a star is born. Every star in the night sky, including our sun, formed in a molecular cloud billions of years ago. By interstellar standards, molecular clouds are dense. They might contain hundreds or even thousands of atoms per cubic centimeter. Some of the densest cores, the regions where stars are actively forming, can reach millions of atoms per cubic centimeter. But remember, Earth's atmosphere contains 25 quintillion molecules per cubic centimeter. Even the densest molecular cloud cores are still trillions of times emptier than air. A molecular cloud is considered dense only by the incredibly sparse standards of space. By any terrestrial measure, it's still almost perfectly empty. Molecular clouds make up only about 1% of the interstellar medium's volume. They're rare concentrations of matter, islands of relative density in an ocean of near nothingness. The cold neutral medium is the next phase. This consists of atomic hydrogen gas, not molecular hydrogen, cooled to temperatures between 50 and 100 Kelvin. The density is lower than molecular clouds, typically around 20 to 50 atoms per cubic centimeter. The cold neutral medium makes up about 1 to 5% of the interstellar medium's volume. It often exists in sheets and filaments surrounding molecular clouds, a transition zone between the densest regions and the sparser material beyond. The warm neutral medium is more diffuse still. This is hydrogen gas at temperatures between 6,000 and 10,000 Kelvin, with densities of only about 0.2 to 0.5 atoms per cubic centimeter. At these temperatures, the hydrogen is still atomic, not ionized. The electrons remain attached to the protons. The warm neutral medium fills about 10 to 20% of interstellar space. Then, there's the warm ionized medium. This has similar temperatures to the warm neutral medium, around 8,000 Kelvin, but the hydrogen is ionized. The electrons have been stripped from the atoms, creating a plasma of free electrons and protons. The density is similar to the warm neutral medium, about 0.2 to 0.5 particles per cubic centimeter. The warm ionized medium fills a substantial fraction of the galaxy's volume, somewhere between 20 and 50%. It exists in a thick disk around the galactic plane, and also in a more diffuse halo extending above and below. But the dominant phase of the interstellar medium by volume is the hot ionized medium. This is gas that's been superheated to temperatures of hundreds of thousands, or even millions of Kelvin. At these extreme temperatures, all the hydrogen is completely ionized. So are heavier elements, stripped of multiple electrons. This is a fully ionized plasma, incredibly hot and incredibly sparse. The density of the hot ionized medium is astonishingly low, about 0.003 atoms per cubic centimeter. That's 3 atoms in every 1,000 cubic centimeters. 3 atoms in a volume about the size of a large grapefruit. This hot gas is created primarily by supernova explosions. When a massive star dies, it explodes with tremendous energy, releasing as much energy in seconds as the sun will produce in its entire 10 billion year lifetime. This explosion creates a shock wave that expands outward into the surrounding interstellar medium at thousands of kilometers per second. As the shock wave passes through, it heats the gas to millions of degrees and sweeps it outward, creating a bubble of extremely hot, extremely sparse material. Over time, these bubbles expand, cool, and eventually merge. Multiple supernovae in the same region can create larger and larger voids. The hot ionized medium fills somewhere between 50 and 70% of interstellar space by volume. It's the dominant environment in the galaxy, the background against which the denser phases exist. Our own solar system sits inside one of these hot bubbles. It's called the local bubble, and it's a region about 300 light years across, where the interstellar medium has been swept out by ancient supernova explosions. The local bubble was probably carved by multiple supernovae, occurring over the past 10 to 20 million years, possibly associated with a nearby stellar association that has since dispersed. Inside the local bubble, the interstellar medium is even sparser than usual. Densities as low as 0.001 atoms per cubic centimeter have been measured. We live in a cosmic void, a bubble of near nothingness carved into the already sparse interstellar medium by the violent deaths of ancient stars. Now, let me try to help you visualize just how empty this really is. Because numbers like 0.003 atoms per cubic centimeter don't connect to anything in human experience, let me try some thought experiments. Consider the hot ionized medium with its density of about 0.003 atoms per cubic centimeter. At this density, each atom occupies, on average, about 330 cubic centimeters of space. That's roughly the volume of a soda can. So if you imagine dividing space into soda can-sized volumes, each one would contain, on average, one hydrogen atom, or more precisely, one ion, since the hydrogen is fully ionized at these temperatures. But atoms are tiny, extraordinarily tiny. A hydrogen atom has a diameter of about 100 millionth of a centimeter. That's 0.0 centimeters. Written in scientific notation, about 10 to the negative 8th centimeters. An atom is so small that you could line up 10 million of them across a single millimeter. The volume of a hydrogen atom is about 10 to the negative 39th cubic centimeters. If you compare this to the 330 cubic centimeters that each atom has to itself in the hot ionized medium, you find that the atom occupies about 1 sextillionth of its available space. The other 999.99999999999999999% is absolutely nothing. Pure vacuum. The emptiest empty that exists. Let me try another way to visualize this. Imagine scaling up a hydrogen atom to the size of a marble, about 1 centimeter in diameter. At this scale, how far away would the nearest hydrogen atom be in the hot ionized medium? About 7,000 kilometers, over 4,000 miles, roughly the distance from New York to London. You'd have a marble floating in space, and the nearest other marble would be on another continent. And between them, nothing. Absolutely nothing. Not air, not gas, not anything. Just void stretching across thousands of miles. Think about holding a marble in New York and trying to imagine another marble in London. That's how far apart atoms are in the hot ionized medium, when scaled to sizes we can see. You'd be alone in an emptiness so complete that even the word emptiness fails to capture it. The best vacuum chambers on Earth, the ones used for semiconductor manufacturing, particle physics experiments, and testing spacecraft components, can achieve what scientists call ultra-high vacuum. This corresponds to pressures of about 100 million molecules per cubic centimeter. That sounds impressively low, and by Earth standards, these are the emptiest spaces humans have ever created. But even ultra-high vacuum is still roughly 30 billion times denser than the hot ionized medium. 30 billion. We cannot create anything close to the emptiness of interstellar space in our laboratories. The technology simply doesn't exist. The interstellar medium is emptier than anything humans have ever experienced or created, by a factor of tens of billions. The technology simply doesn't exist. The interstellar medium is emptier than anything humans have ever experienced or created, by a factor of 100 trillion or more. This isn't just academically interesting. It has real implications for what interstellar travel would be like. If you could somehow transport yourself into interstellar space, far from any star, what would you experience? Let's imagine you're floating in the hot ionized medium, somewhere in the vast emptiness between stellar systems. What would your senses tell you? Sight. You would see nothing but stars. Not stars crowded together like in science fiction movies, but distant points of light scattered across an absolutely black background. No nebulae visible to the naked eye, no glowing gas clouds, just pinpricks of light against infinite darkness. The density of matter around you would be so low that light would travel essentially unimpeded. There would be no scattering, no diffusion, no haze, just perfect clarity and perfect blackness, punctuated by the cold light of distant suns. On Earth, we're never in true darkness. Even on the darkest night, in the most remote wilderness, far from any artificial light, there's still illumination. Starlight. The faint glow of the Milky Way. The zodiacal light from dust in the solar system. Air glow from the upper atmosphere. Our eyes adapt, and we can see, at least dimly. In interstellar space, if you turned off your spacecraft's lights, the darkness would be more complete than anything humans have ever experienced. There would be no ambient glow, no scattered light from any source. Just the stars themselves, points of light in an ocean of black. Your eyes might never fully adapt, because there would be nothing to adapt to. Just darkness, deeper than any cave on Earth, darkness with no bottom and no end. Touch. You would feel nothing. The atoms around you would be so sparse that they would essentially never contact your body. In the hot ionized medium, with its density of 0.003 atoms per cubic centimeter, a human body would encounter only about a few thousand atoms per second, passing through its entire surface area. You wouldn't feel this. The atoms are too few and too light. There would be no pressure, no resistance, no sensation of anything touching you. Just emptiness against your skin. Sound. There would be none. Sound requires a medium to travel through. Sound waves are pressure variations transmitted through collisions between particles. In air, molecules bounce off each other billions of times per second, transmitting vibrations from one place to another. This is how sound propagates. In the interstellar medium, atoms are so far apart that they essentially never collide with each other. There's no mechanism for pressure waves to propagate. Sound cannot exist. If you screamed in interstellar space, without a spacesuit, obviously you couldn't. But hypothetically, if you could, the sound would go nowhere. The vibrations from your vocal cords would enter the void and simply stop. There would be nothing to carry them. You could scream for eternity and no one would hear, not because they're far away, but because sound itself cannot travel. The silence would be absolute. Not the silence of a quiet room, which still contains the subtle sounds of air moving, of distant traffic, of your own heartbeat. True silence. The absence of the possibility of sound. An environment where the very concept of sound has no meaning. This is the sensory reality of interstellar space. Darkness without limit, silence without end, emptiness so complete that your body would never feel it. An environment of profound sensory deprivation, unlike anything that exists on Earth. But the emptiness of interstellar space doesn't mean it's safe. There are hazards out there in the void, invisible but dangerous, and the most significant of these hazards are cosmic rays. Cosmic rays are high-energy particles that stream through the galaxy in all directions. Despite the name, they're not rays like light rays. They're actual particles, mostly protons, but also heavier atomic nuclei like helium, carbon, oxygen, and even iron. What makes them special is their energy. Cosmic rays travel at velocities close to the speed of light, carrying enormous kinetic energy packed into tiny packages of matter. Cosmic rays come from various sources. The sun emits low-energy cosmic rays, really just the most energetic particles of the solar wind, with energies in the kilo-electron-volt to mega-electron-volt range. More energetic cosmic rays in the giga-electron-volt to tera-electron-volt range come from supernova explosions. When a massive star dies, the shockwave from the explosion can accelerate particles to tremendous speeds. These particles then escape into interstellar space and wander the galaxy for millions of years. The most energetic cosmic rays of all, the ultra-high energy cosmic rays with energies exceeding 10 to the 18th electron volts, remain mysterious. We don't fully understand where they come from. Perhaps from active galactic nuclei, the supermassive black holes at the centers of distant galaxies. Perhaps from gamma ray bursts, the most energetic explosions in the universe. Perhaps from sources we haven't discovered yet. These particles carry so much energy that a single proton, an object far too small to see, can have the kinetic energy of a baseball thrown at highway speeds. Cosmic rays don't travel in straight lines through the galaxy. They're charged particles, and charged particles are deflected by magnetic fields. The galaxy has a weak but extensive magnetic field that causes cosmic rays to spiral and bounce, following complex paths through the interstellar medium. A cosmic ray, produced by a supernova, might wander through the galaxy for millions of years, deflected this way and that by magnetic irregularities, before finally escaping into intergalactic space. The cosmic rays we detect today have been traveling for eons. On Earth, we're protected from most cosmic rays by two shields. First, Earth's magnetic field deflects many charged particles, especially lower energy ones, steering them toward the poles where they cause the auroras. Second, our atmosphere absorbs and fragments the cosmic rays that make it through the magnetic field. When a high-energy cosmic ray hits the upper atmosphere, it collides with air molecules and creates a shower of secondary particles. Most of these secondary particles are absorbed before reaching the ground. In interstellar space, there's no such protection. Any spacecraft or traveler would be exposed to the full flux of galactic cosmic rays. And this exposure would be dangerous. When a high-energy particle passes through living tissue, it ionizes atoms along its path. It strips electrons from molecules, breaking chemical bonds, damaging DNA, killing cells. A single cosmic ray impact can cause mutations that lead to cancer. It can kill neurons in the brain. It can damage the delicate tissues of the eyes, leading to cataracts. The danger isn't from any single cosmic ray, it's from the cumulative exposure over time. In interstellar space, cosmic rays would constantly bombard any spacecraft or person. The flux varies depending on where you are in the galaxy and what the sun is doing, but it's always present. The longer the journey, the more exposure, and the greater the risk. Any interstellar spacecraft would need substantial shielding against cosmic rays. But shielding is heavy, and weight is the enemy of interstellar travel. Every kilogram of shielding must be accelerated along with the rest of the spacecraft, requiring more fuel and more energy. There are theoretical designs using water tanks or hydrogen-rich materials that could provide protection, but they all add mass and complexity. For short trips to the Moon or Mars, cosmic ray exposure is a manageable risk. But for journeys of decades or centuries to other stars, it becomes a serious challenge. The longer you travel through interstellar space, the more cosmic rays pass through your body, and the greater the probability of serious harm. Now, let me talk about another component of the interstellar medium: dust. It's far less abundant than the gas, but it has effects out of proportion to its scarcity. Interstellar dust consists of tiny solid particles, typically sub-micrometer in size. They're made of various materials depending on where they formed. Silicate grains, similar to the minerals in Earth's rocks, are common. Carbonaceous grains, including complex organic compounds, are also abundant. In the colder regions of space, dust grains accumulate mantles of ice, water ice, carbon dioxide ice, and other frozen volatiles. The ratio of dust to gas in the interstellar medium is roughly 1 dust grain per 100 billion hydrogen atoms. By mass, dust makes up only about 1% of the interstellar medium. It's rare, but dust has important effects. Dust absorbs and scatters light, particularly at shorter wavelengths. When you look at the Milky Way stretching across the night sky, the dark patches you see, especially toward the galactic center, aren't regions with fewer stars. They're regions where dust clouds block our view of the stars behind them. The dust grains absorb visible light from distant stars and re-radiate that energy at longer wavelengths, in the infrared. This is why infrared telescopes, like the James Webb Space Telescope, are so valuable for studying the galaxy. They can peer through the dust to reveal stars and structures invisible to optical instruments. Dust also plays a crucial role in interstellar chemistry. The surfaces of dust grains act as catalysts, providing sites where atoms can meet and form molecules. In the frigid interiors of molecular clouds, where temperatures hover just above absolute zero, atoms that land on dust grains can stick and eventually encounter other atoms, forming molecules that couldn't form in the gas phase. Complex organic molecules, including amino acids and other compounds relevant to the origin of life, have been detected in interstellar space. Some scientists believe that organic molecules formed on interstellar dust grains were delivered to the early Earth by comets and asteroids, potentially seeding our planet with the building blocks of life. But for any spacecraft traveling through interstellar space, dust presents a hazard. At low speeds, this hazard is negligible. Dust grains are incredibly sparse. In the hottest, emptiest regions of interstellar space, you might find only a few dozen grains per cubic kilometer. In denser regions, perhaps thousands per cubic kilometer. But even thousands of grains scattered through a cubic kilometer means vast distances between each speck of dust. A spacecraft traveling at ordinary speeds would encounter very few grains over any reasonable journey within the solar system. But at the speeds necessary for interstellar travel, even rare dust grains become dangerous projectiles. Kinetic energy scales with a square of velocity. A grain moving twice as fast has 4 times the energy. A grain moving 10 times as fast has 100 times the energy. At 10% of the speed of light, about 30,000 kilometers per second, a dust grain weighing 1 nanogram, 1 billionth of a gram, would strike with an energy of about 450 joules. That's roughly the energy of a small firecracker. Not catastrophic for a large spacecraft, but definitely noticeable. A dust grain weighing 1 microgram, 1 millionth of a gram, would impact with about 450 kilojoules of energy. That's comparable to about 100 grams of TNT. This could cause significant damage to spacecraft components, puncturing thin walls, destroying sensors, degrading surfaces. Larger grains, while rarer, would be even more dangerous. A milligram grain, still invisible to the naked eye, would carry the energy of about 100 kilograms of TNT. Such an impact could be catastrophic, potentially destroying an entire spacecraft. The good news is that large grains are very rare. The interstellar medium is dominated by smaller particles, but over a journey of light years, even rare events become probable. Any interstellar spacecraft would need some kind of protection, whether passive shielding to absorb impacts, or active systems to detect and deflect incoming particles. This is yet another engineering challenge added to the already formidable list. Finally, let me tell you about something even stranger that threads through interstellar space: magnetic fields. The galaxy has a magnetic field. It's incredibly weak by earthly standards. The strength is typically a few microgauss, which is about 500,000 times weaker than Earth's magnetic field, and roughly 1 billion times weaker than a simple refrigerator magnet. If you could somehow sense magnetic fields directly, the galactic magnetic field would be utterly imperceptible. But this weak field extends across thousands of light years. Its total extent is vast, threading through the spiral arms, permeating the space between stars, influencing the behavior of charged particles throughout the galaxy. The galactic magnetic field isn't simple like a bar magnet with neat north and south poles. It's complex and tangled, with different strengths and orientations in different regions. It generally follows the spiral structure of the galaxy, stronger in the spiral arms where gas and dust are more concentrated. It's also turbulent, with irregularities and fluctuations at all scales. This magnetic field channels the flow of charged particles, including cosmic rays. Cosmic rays spiral along magnetic field lines, deflected by irregularities, bouncing back and forth as they wander through the galaxy. The magnetic field also affects the structure of the interstellar medium itself. Ionized gas tends to flow along magnetic field lines rather than across them. The shapes of molecular clouds and other structures are influenced by the local magnetic field orientation. For future spacecraft traveling through interstellar space, the galactic magnetic field could be both friend and foe. On one hand, it might be possible to use magnetic effects for propulsion or navigation. On the other hand, the field is so weak and so variable that predicting its behavior precisely would be extremely difficult. Any technology that relies on magnetic interactions would need to account for a complex, turbulent, and poorly mapped field extending across light years of space. So, what have we learned about the great emptiness? Interstellar space is not quite empty. It contains the interstellar medium, a sparse mixture of gas and dust that fills the voids between stars. But this medium is so thin, so sparse, so incredibly rarefied that it challenges our understanding of what emptiness means. 1 atom per cubic centimeter on average. In the hottest regions, 0.003 atoms per cubic centimeter. Densities 100 trillion times lower than the best vacuums we can create on Earth. The interstellar medium has structure, molecular clouds where stars are born, cold neutral gas in filaments and sheets, warm gas filling large volumes, hot gas in bubbles carved by supernovae. Our own solar system sits in one such bubble, the local bubble, a void 300 light-years across, where ancient stellar explosions swept away most of the surrounding gas. If you could experience interstellar space directly, you would find darkness more complete than any cave on Earth, silence more absolute than any soundproofed room, emptiness so profound that your senses would have nothing to report, environment of sensory deprivation beyond anything in human experience. But this emptiness is not safe. Cosmic rays stream through the void, high-energy particles that would damage living tissue and spacecraft components over time. Dust grains, though rare, become dangerous projectiles at interstellar velocities. The galactic magnetic field threads through everything, weak but pervasive, influencing the paths of charged particles and the structure of the medium itself. Interstellar space is cold, empty, dark, and flooded with invisible radiation. It's an environment utterly indifferent to life. Not hostile exactly. Hostility implies intent, implies caring. Interstellar space doesn't care. It simply is. Vast, empty, unconcerned with whether anything travels through it or survives the journey. And yet, this is what we must cross to reach other stars. This is the ocean between the islands of light. If humanity ever wants to become a multistellar species, if we ever want to reach worlds, orbiting other suns, we must find ways to traverse this void. We must build vessels that can survive the radiation, the dust impacts, the decades or centuries of travel through nothingness. Can we do it? Is it possible to cross the great emptiness? That's the question we'll explore next. The void awaits. Let's see what it would take to traverse it. Science fiction has always been in love with the stars. Warp drives that bent space around a starship. Hyperspace jumps that bypass normal space entirely. Wormholes that create shortcuts across the galaxy. Cryogenic sleep that lets travelers skip the boring parts of centuries-long journeys. Generation ships the size of cities, carrying thousands of colonists to distant worlds. In our stories, we've imagined countless ways to cross the interstellar gulf. But stories and physics are different things. What does physics actually allow? What methods of interstellar travel are grounded in real science rather than wishful thinking? And what challenges would any of these methods face? The gap between our dreams and our current reality is immense. We've sent robots to every planet in our solar system. We've landed humans on the moon. We've built space stations where people live for months at a time. By any historical standard, our achievements in space are remarkable. But interstellar travel is a challenge of an entirely different order. The distances involved are so vast, the energy requirements so extreme, that even our greatest accomplishments barely scratch the surface of what would be needed. And yet, there are real proposals. Serious scientists and engineers have studied methods that might actually work, at least in principle. Some could potentially be built with near-future technology. Others would require advances we haven't made yet, but advances that don't violate any known laws of physics. The dream of reaching the stars isn't just fantasy. It's an engineering problem. An extraordinarily difficult engineering problem, but an engineering problem nonetheless. Let's explore what it would actually take to cross the void. We established earlier that the distances between stars are almost incomprehensibly vast. Proxima Centauri, our nearest stellar neighbor, is over 4 light-years away. Our fastest spacecraft, the Parker Solar Probe, would take roughly 6,500 years to cover that distance. Voyager 1, currently the most distant human-made object, would need about 73,000 years. These numbers tell us something crucial. We don't need to be a little bit faster. We need to be dramatically revolutionary faster, orders of magnitude faster. If our best current technology requires tens of thousands of years to reach the nearest star, then incremental improvements won't help. Doubling our speed would still mean journeys of thousands of years. Even increasing our speed by a factor of 10 would leave us with centuries of travel time. To reach another star within a human lifetime, or even within a few human lifetimes, we need spacecraft traveling at significant fractions of the speed of light. Not 0.01% of light speed, like our current probes, not 0.1%. We need 1%, 5%, 10%, or more. This is where the real challenge lies. Getting from our current capabilities to even 1% of light speed represents an improvement of more than 100 times over our fastest spacecraft. Getting to 10% of light speed means improving by more than 1,000 times. This isn't like the history of aviation, where each decade brought faster planes until we reach the limits of atmospheric flight. This is a fundamental shift. A leap from crawling to sprinting, from paddling a canoe to piloting a rocket. The technologies that could enable such speeds exist in theory. Some have been tested in small ways, but building actual interstellar spacecraft remains beyond our current capabilities. The question is whether it will always remain beyond us, or whether future generations might find ways to cross the gulf. Let's start with one of the most elegant concepts for space propulsion, the solar sail. The basic idea is simple. Light exerts pressure. When photons strike a surface, they transfer a tiny amount of momentum. You don't notice this in everyday life because the pressure is incredibly small. But in the vacuum of space, where there's no air resistance, even tiny forces can accumulate over time. A large, lightweight sail could catch the pressure of sunlight and gradually accelerate, just as a sailing ship catches the wind. The beautiful thing about solar sails is that they require no fuel. The propulsion comes from starlight itself. A spacecraft with a solar sail could accelerate continuously as long as it remained close enough to a star for the light pressure to be significant. No need to carry propellant. No need to worry about running out of fuel. Just unfurl your sail and let the light push you. This isn't science fiction. Solar sails have actually been tested. In 2010, the Japanese space agency JAXA launched Icaros, a spacecraft with a solar sail about 14 meters across. Icaros successfully demonstrated that solar sail propulsion works. The acceleration was tiny, but it was real and measurable. The concept had been proven. More advanced designs envision sails hundreds or thousands of meters across, made of materials only a few molecules thick. These enormous gossamer-thin structures could potentially accelerate small payloads to impressive speeds. Some proposals suggest that solar sails could reach velocities of several hundred kilometers per second, fast enough to escape the solar system in years rather than decades. But solar sails have a fundamental limitation. The pressure of sunlight decreases with the square of distance from the sun. At Earth distance, sunlight provides about 9 micronewtons of force per square meter of sail. At the orbit of Mars, about 1.5 times farther from the sun, the pressure drops to about 4 micronewtons. At Saturn's orbit, roughly 10 times further than Earth, the pressure is only about 1% of what it is here. By the time you reach Pluto, the pressure has dropped to less than 1/16th of 1%. Solar sails work well for travel within the inner solar system. They could potentially be very effective for missions to Mercury, Venus, or Mars. But for interstellar travel, where you need to accelerate far from any star, sunlight alone isn't enough. The sail would accelerate while close to the sun, then coast through the darkness between stars with no further push. This limitation led to a clever idea. What if you didn't rely on sunlight? What if you provided your own light source, a powerful laser that could push a sail even when it was far from the sun? This is the concept behind Breakthrough Starshot, one of the most ambitious interstellar proposals currently being developed. Announced in 2016 by physicist Yuri Milner and the late Stephen Hawking, Breakthrough Starshot proposes using an array of powerful ground-based lasers to accelerate small spacecraft to about 20% of the speed of light. The concept is elegant. You build a spacecraft that's incredibly small and light, essentially a computer chip with a camera and communication equipment, weighing about 1 gram. This tiny craft, called a star chip, is attached to a light sail about 4 meters across but incredibly thin, perhaps only a few hundred atoms thick. The entire package, chip and sail together, weighs only a few grams. On Earth or in orbit, you build an array of powerful lasers capable of producing about 100 gigawatts of coherent light. You point this array at the star chip and its sail, focusing an intense beam of light that pushes the sail with tremendous force. For about 10 minutes, the laser array fires, accelerating the tiny spacecraft at tens of thousands of times Earth's gravity. By the end of this brief but intense acceleration phase, the star chip is traveling at 20% of light speed, about 60,000 kilometers per second. At this velocity, the journey to Proxima Centauri takes about 20 years. The star chip can't slow down. There's no way to decelerate something so small, traveling so fast. It flies through the Proxima Centauri system at tremendous speed, perhaps having only hours to take photographs and measurements before it's passed and continuing into the void. But during those hours, it could transmit data back toward Earth using a tiny onboard laser. That signal, traveling at light speed, would take another 4 years to reach us. Total time from launch to receiving data, about 24 years. Within a human lifetime, conceivable. But the engineering challenges are extraordinary. The laser array would need to be thousands of times more powerful than anything that currently exists. 100 gigawatts is roughly the peak electricity consumption of a medium-sized country. Generating this much power and focusing it into a coherent beam that can track a spacecraft accelerating away at tremendous speed is far beyond our current capabilities. The sail materials present another challenge. To survive the intense laser illumination without vaporizing, the sail must reflect almost all the light that hits it. It must be incredibly thin to keep the mass low, yet strong enough not to tear. Materials with these properties are only beginning to be developed in laboratories. Manufacturing a sail 4 meters across with uniform properties throughout is a challenge we haven't solved. The star chip itself must survive acceleration forces of tens of thousands of Gs. It must operate after decades of exposure to cosmic rays and interstellar dust impacts. It must transmit data across 4 light years of space using equipment smaller than your thumbnail. And it must do all this autonomously with no possibility of repair or intervention. Then there's the problem of actually hitting the target. Proxima Centauri is a moving target, and the star chip has no way to adjust its course after the initial acceleration. The aiming must be precise from the start. Any error, even a tiny fraction of a degree, would cause the spacecraft to miss its target by millions of kilometers. Despite all these challenges, Breakthrough Starshot represents what might actually be achievable within the next few decades if we commit sufficient resources. The physics works. No new laws of nature need to be discovered. It's engineering. Extraordinarily difficult engineering, but engineering nonetheless. This is the most credible near-term proposal for sending anything to another star. But what about sending humans? Here's where the challenge becomes truly daunting. A star chip weighs about 1 gram. A human being weighs about 70 kilograms. That's a factor of 70,000. And you can't just send a naked human through space. You need a spacecraft to contain them. Life support systems to provide air, water, and temperature control. Food for decades of travel. Radiation shielding to protect against cosmic rays. Living space for psychological health. Probably multiple humans, because one person alone for decades would likely go insane. Medical facilities. Repair equipment. Redundant systems for everything critical. A minimally viable crewed interstellar spacecraft might weigh on the order of 100,000 tons. Perhaps much more. This is roughly the mass of a large aircraft carrier, and you need to accelerate this mass to a significant fraction of light speed. The energy requirements are staggering. Kinetic energy scales with mass and with the square of velocity. To accelerate 100,000 tons to 10% of light speed would require approximately 4 times 10 to the 23rd joules of energy. For perspective, this is roughly equivalent to the total energy consumption of human civilization for several decades. All of that energy concentrated into accelerating one spacecraft. And that's just to get up to speed. You also need to slow down when you arrive. Otherwise, you fly past your destination at 10% of light speed, unable to stop, unable to enter orbit, unable to land. Slowing down requires just as much energy as speeding up. So double the energy requirement. Where would this energy come from? How would you deliver it to a spacecraft? These questions don't have easy answers. The mass problem is fundamental to crewed interstellar travel. It's not just a matter of building bigger rockets or more powerful engines. It's a question of whether the energy requirements are even achievable by any civilization, much less ours. One approach that takes the mass problem seriously is nuclear pulse propulsion, studied extensively in the 1950s and 60s under the name Project Orion. The concept sounds insane at first. You detonate nuclear bombs behind your spacecraft and ride the shockwaves, but the physics actually works. Nuclear explosions release enormous amounts of energy. If you can channel even a fraction of that energy into pushing a massive plate, you can achieve accelerations far beyond what chemical rockets provide. The Project Orion design used a pusher plate, a massive disc at the rear of the spacecraft. Nuclear bombs would be ejected behind the plate and detonated. The explosion would vaporize a propellant material, creating a plasma that would slam into the pusher plate and push the spacecraft forward. Shock absorbers would smooth out the ride, converting the violent pulses into steady acceleration. The numbers were impressive. Project Orion estimated that such a spacecraft could reach velocities of 3 to 5% of light speed. At these speeds, the journey to Proxima Centauri would take roughly 80 to 140 years. Still a long time, but within the span of a few human generations. People born on the ship might live to see the destination. Project Orion was never built. The Partial Nuclear Test Ban Treaty of 1963 prohibited nuclear explosions in space, effectively ending the program. But the physics was sound. The concept worked on paper, and there's no fundamental reason it couldn't work in practice. The challenges are practical and political rather than physical. You would need thousands of nuclear bombs. The radiation from the explosions would be intense, requiring heavy shielding. International treaties would need to be rewritten or abandoned. And you would need the same number of bombs to decelerate at your destination, meaning you must carry your entire supply for both acceleration and braking from the start. Project Orion represents a path to interstellar travel that could conceivably be built with technology not too far beyond what we have today. It would be expensive, politically difficult, and ethically controversial, but it wouldn't require any new physics. It's an engineering challenge, not a scientific one. More advanced propulsion concepts look to fusion and antimatter. Fusion propulsion would use controlled nuclear fusion reactions to generate thrust. Instead of detonating bombs, you would have a reactor that continuously fuses hydrogen isotopes, producing a stream of high-energy particles that provide thrust. Fusion releases far more energy per unit mass than fission. The fuel, primarily hydrogen isotopes like deuterium and tritium, is relatively abundant. In principle, fusion-powered spacecraft could achieve higher speeds and better efficiency than nuclear pulse designs. The problem is that we haven't achieved practical fusion yet. Decades of research have brought us closer, but controlled fusion that produces more energy than it consumes remains elusive. Fusion for propulsion is even harder than fusion for electricity generation, because you need to direct the energy efficiently into thrust rather than just capturing heat. Practical fusion propulsion might be decades away, or it might be centuries away. We simply don't know. Antimatter propulsion is the ultimate theoretical option. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy according to Einstein's famous equation. This is the most efficient energy release possible. 1 gram of antimatter annihilating with 1 gram of matter releases energy equivalent to roughly 43 kilotons of TNT. A spacecraft with an antimatter drive could theoretically achieve very high speeds, perhaps significant fractions of light speed. The fuel efficiency would be unmatched by any other known propulsion method. But antimatter is extraordinarily difficult to produce. It doesn't exist naturally in significant quantities. You have to create it in particle accelerators, antiproton by antiproton, positron by positron. The total amount of antimatter ever produced by all the particle accelerators in the world is estimated at roughly 20 nanograms, 20 billionths of a gram, enough to power a flashlight for about half a second. To power an interstellar mission, you would need kilograms or tons of antimatter. With current technology, producing this much would cost more than the entire economic output of human civilization. Antimatter propulsion isn't just difficult, it's currently so far beyond our capabilities that it might as well be magic. Perhaps future technologies will make antimatter production practical, perhaps not. For now, it remains firmly in the realm of speculation. Given the difficulties of fast interstellar travel, some have proposed a different approach entirely. Don't try to make the journey fast. Accept that it will take centuries and design accordingly. Build a generation ship. A generation ship would be a massive vessel, essentially a small world, designed to sustain a human population for hundreds of years. People would be born on the ship, live their entire lives there, and die there. Their children and grandchildren would continue the journey. Eventually, after many generations, descendants of the original crew would arrive at the destination. This approach sidesteps the propulsion problem to some extent. You don't need to reach high speeds. Even at 1% of light speed, the journey to Proxima Centauri takes about 425 years. That's many generations, but it's finite. A ship traveling at more modest speeds, achievable with nuclear pulse propulsion or advanced chemical rockets, might take thousands of years, but it would eventually arrive. But generation ships raise profound challenges that go beyond engineering. Ethical questions. Is it moral to create people who will spend their entire lives confined to a spacecraft? Who never chose to be born into this situation? Who will never see open skies or breathe unrecycled air? Sociological questions. How do you maintain a functioning society for centuries in a confined space? How do you prevent social breakdown, conflict, tyranny, or revolution? Psychological questions. What is the effect on the human psyche of knowing you were born in a metal box and will die in that same box, that you will never reach the destination your ancestors chose? Technical questions abound as well. How do you maintain a closed ecosystem for centuries? Every molecule of air, every drop of water, every nutrient must be recycled indefinitely with essentially perfect efficiency. Any significant loss accumulates over time and eventually becomes fatal. How do you handle equipment failures? Over centuries, everything breaks. You must be able to manufacture replacement parts for any critical system using only the resources on board. How do you prevent genetic problems from inbreeding in a small population? How do you handle medical emergencies with no possibility of outside help? Generation ships are not just engineering challenges, they're social, psychological, and philosophical challenges. Building the ship might be the easy part. Building a society that can function inside it for centuries might be the true obstacle. Even if we solve the propulsion problem, even if we build spacecraft capable of carrying humans to other stars, we face a challenge that no technology can overcome: the problem of time and isolation. Consider a spacecraft traveling at 10% of light speed, a velocity far beyond our current capabilities, but theoretically achievable with advanced propulsion. At this speed, the journey to Proxima Centauri takes about 43 years. A person who boards the ship at age 20 would arrive at age 63, assuming they survived the journey. But during those 43 years, communication with Earth would become increasingly difficult. Radio signals and laser communications travel at light speed. When the ship is 1 light year from Earth, messages take 1 year each way. Any question requires a 2-year wait for an answer. By the time the ship is halfway to Proxima Centauri, over 2 light years away, the round trip for messages exceeds 4 years. What does this mean practically? If something goes wrong on the ship, if there's a medical emergency, a mechanical failure, a navigational crisis, the crew cannot call home for help and receive timely assistance. By the time Earth learns of the problem, years will have passed. By the time any advice reaches the ship, years more will have gone by. The situation will have resolved one way or another long before help could arrive. The crew must be completely self-sufficient. They must have the knowledge, skills, and resources to handle any conceivable problem using only what they brought with them. They cannot rely on resupply. They cannot rely on expert consultation. They cannot rely on rescue. They are alone, truly alone, in a way no humans have ever been. The psychological implications are profound. Crew members would watch Earth recede, first a bright dot, then a faint star, then lost among the countless stars of the Milky Way. Messages from home would arrive bearing news increasingly distant in time. Friends and family left behind would age, live their lives, and die, all compressed into sporadic, years-delayed updates. The crew would know that the world they left has moved on without them, that they have become ghosts to everyone they once knew. Children born on the ship would grow up knowing Earth only as a story, a mythology from before their birth. They would be citizens of nowhere, belonging neither to the world their grandparents left, nor to the world they might someday reach. Their entire existence would unfold in transit, in the space between origins and destinations. And even when the ship arrives, if it arrives, the isolation doesn't end. Any colony established around Proxima Centauri would remain over 4 light years from Earth. Every conversation would have an 8-year delay. The colony couldn't participate in Earth politics, economy, or culture in any real-time way. It would inevitably develop its own society, its own traditions, its own identity. Within generations, it might become unrecognizable to people on Earth. This is what interstellar distances truly mean. Even if we solve every engineering problem, even if we build ships that can cross the light years, we cannot shrink the void. We cannot make the journey faster than light allows. We cannot escape the fundamental isolation that interstellar distances impose. The speed of light isn't just a speed limit. It's an isolation barrier. It means that any human presence among the stars would be fragmented by necessity. Not one civilization spanning the galaxy, but many isolated pockets of humanity, each going its own way, each developing independently, connected only by messages that take years or decades to traverse the darkness between them. This isn't necessarily a tragedy. Perhaps it's simply the nature of intelligent life in a vast universe. Perhaps isolation is the price of expansion. Perhaps the diversity that results from separated development is a strength rather than a weakness. But it's important to understand what we're contemplating when we dream of reaching the stars. We're not dreaming of a galactic neighborhood where travel between worlds is routine. We're dreaming of casting seeds into the void, seeds that will grow into something we may never see, on worlds we may never visit, among descendants who will become strangers to us. The void can be crossed. The physics allows it. The engineering is extraordinarily difficult, but not impossible. But even when we cross it, the void remains. The distances don't shrink. The isolation doesn't end. That is the true nature of interstellar space, and any dream of reaching the stars must reckon with it. We've traveled far together tonight. We've explored the vast distances between stars, those light years of emptiness that separate one sun from another. We've descended into the great emptiness itself, the interstellar medium with its sparse atoms and wandering cosmic rays, its darkness and silence and cold. We've examined what it would take to cross that void, the propulsion systems that might work, and the challenges that await any traveler. Now let's step back. Let's think about what all of this means. Not just the physics and engineering, but the deeper implications. What do interstellar distances mean for the search for life beyond Earth? What do they mean for humanity's place in the cosmos? What do they tell us about our future as a species? These aren't just abstract philosophical questions. They're deeply practical. How we answer them shapes how we think about space exploration, about the allocation of resources, about our responsibilities to future generations. The scale of interstellar space isn't just a scientific curiosity. It's a fundamental constraint on what's possible, and understanding it helps us understand ourselves. Let's begin with a question that has fascinated humanity for centuries. Are we alone in the universe? The universe is unimaginably vast. The observable universe, the part we can see from Earth, contains approximately 2 trillion galaxies. Not million, trillion. 2,000 billion galaxies scattered across a sphere, 93 billion light years in diameter. Each of those galaxies contains anywhere from millions to trillions of stars. The Milky Way, our home galaxy, contains somewhere between 100 billion and 400 billion stars. Some galaxies are smaller, some are larger, but the average is in the hundreds of billions. Do the multiplication and the numbers become staggering. The total number of stars in the observable universe is estimated at around 200 billion trillion. That's a 2 followed by 23 zeros. More stars than grains of sand on all the beaches of Earth. More stars than seconds that have elapsed since the Big Bang. And most of those stars have planets. The Kepler Space Telescope and other planet-hunting missions have revealed that planets are common, not rare. On average, every star in our galaxy has at least one planet. Many have several. The total number of planets in the observable universe is probably comparable to the number of stars, perhaps 10 to the 23rd power. 100 billion trillion planets. Even if life is incredibly rare, even if only one planet in a billion develops life, that's still 100 trillion living worlds in the observable universe. Even if only 1 in a billion of those develops intelligent life, that's still 100 billion civilizations. The numbers are so vast that even vanishingly small probabilities produce enormous quantities. This is the basic argument for extraterrestrial life. The universe is so large, contains so many planets, that life should have arisen many times. Not just microbial life, but complex life, intelligent life, technological civilizations. The mathematics seems compelling. We shouldn't be alone. And yet, we have no evidence of anyone else. No confirmed signals from alien civilizations, no artifacts, no megastructures visible in astronomical surveys, no visitors. The universe appears to be silent. This is the Fermi paradox, named after physicist Enrico Fermi, who articulated it over lunch at Los Alamos in 1950. The story goes that Fermi and his colleagues were discussing UFO reports and the possibility of extraterrestrial visitors. Fermi did some quick mental calculations about the age of the galaxy, the number of stars, the time it would take for a civilization to spread, and then asked the famous question, where is everybody? The Milky Way galaxy is about 13 billion years old. Even if intelligent civilizations are rare, even if they arise only once per million years on average, there should have been thousands of civilizations in our galaxy's history. Many of them would have arisen billions of years before us. They would have had enormous head starts, time enough to develop technologies we can barely imagine. If even a small fraction of these civilizations developed interstellar travel, they could have spread across the galaxy. Even at speeds far below light speed, even crawling along at 1% of the speed of light, a civilization could cross the entire Milky Way in about 10 million years. That sounds like a long time. but it's less than 0.1% of the galaxy's age. There's been plenty of time for civilizations to spread everywhere. And yet, when we look at the galaxy, we see no signs of widespread colonization. No Dyson spheres harvesting the energy of stars. No communication signals flooding the radio spectrum. No ancient probes orbiting our sun. Nothing. Just natural stars, natural planets, natural phenomena as far as we can see. This is one of the deepest mysteries in science. Either intelligent life is far rarer than the numbers suggest, or something prevents civilizations from spreading, or they're there but we can't detect them, or they're deliberately avoiding us. Each of these possibilities has profound implications, and none of them is entirely satisfying. Interstellar distances may be part of the answer. The same vast gulfs we've been exploring tonight might explain, at least partially, the Great Silence. Consider what it would take for an alien civilization to make contact with us. They would need to either travel to our solar system or send signals that we could detect. Both are constrained by the physics we've discussed. Even a civilization far more advanced than us, with technologies we can barely imagine, would still face the light speed limit. Nothing can travel faster than light. This isn't a technological limitation that might be overcome with better engineering. It's built into the structure of space-time itself. Any civilization, no matter how advanced, would still need years to cross interstellar distances. Imagine an alien civilization that arose 1 billion years ago somewhere in the Milky Way. 1 billion years is an enormous head start. They could have developed technologies beyond our comprehension. They could have spread throughout the galaxy, but even they couldn't visit every star quickly. The galaxy contains hundreds of billions of stars spread across 100,000 light years. Even traveling at a significant fraction of light speed, visiting all of them would take millions of years. Perhaps they've been spreading for millions of years and simply haven't reached us yet. The galaxy is a big place. Even if civilizations are expanding outward at a healthy clip, there's no guarantee they would have reached our particular corner of the Milky Way in the time available. Or perhaps civilizations don't spread at all. Perhaps the challenges of interstellar travel are so severe that even advanced civilizations choose to stay home. Perhaps energy costs are prohibitive. Perhaps the isolation is too psychologically damaging. Perhaps there's something about interstellar space that makes expansion impractical, something we haven't discovered yet. Or perhaps civilizations spread for a while and then stop. Perhaps they colonize nearby stars, establish a few outposts, and then turn inward. Perhaps they find that the vast distances between colonies lead to fragmentation, to wars, to collapse. Perhaps interstellar empires are inherently unstable, expanding for a time and then retreating to their home systems. Communication faces similar challenges. Radio signals and laser beams travel at light speed, but they weaken with distance. A signal powerful enough to be detected across interstellar distances would require enormous energy. And even if an alien civilization was broadcasting such signals, we would need to be looking in the right direction, at the right frequency, at the right time. The Milky Way is 100,000 light years across. A signal from the far side of the galaxy would take 100,000 years to reach us. By the time it arrived, the civilization that sent it might be long gone. They might have risen, flourished, declined, and vanished, all while the message was in transit. We might receive signals from civilizations that died before the last ice age on Earth. And even if we did receive a signal from a relatively nearby star, meaningful exchange would be painfully slow. If a civilization 50 light years away sent us a message today, we would receive it 50 years from now. If we composed a reply and sent it immediately, they would receive our response 100 years after they sent their original message. Every exchange would span a century. Not dialogue, not conversation. Correspondence across generations. A civilization 500 light years away? 1,000-year round trip for each exchange. 10 exchanges would take 10,000 years, longer than all of recorded human history just for a brief back and forth. This isn't communication in any meaningful sense. It's more like archaeology, studying the records left by distant civilizations, records that are decades or centuries or millennia old by the time they arrive. You could ask a question and your entire civilization might rise and fall before hearing any answer. Perhaps this is the nature of intelligence in the universe, not a galactic community, not a network of civilizations and communication with each other, but isolated islands of awareness, each alone in their corner of the cosmos, separated by distances so vast that meaningful contact is essentially impossible. This is a lonely vision. Humans are social creatures. We evolved in tribes, in communities, in networks of relationships. The idea of being alone, truly alone in the universe, is profoundly unsettling to us. Even if other civilizations exist, if we can never communicate with them, never meet them, never know them, then in practical terms we might as well be alone. But there's another way to look at this. If we are effectively alone, if the distances between civilizations are too great for contact, then what happens here matters enormously. This small planet orbiting this ordinary star might be the only place in this region of the galaxy where awareness exists at all. Our thoughts, our questions, our acts of creativity and compassion might be unique in thousands of light years of space. That's not a burden. It's a privilege. It means that what we do here, how we treat each other and our planet, whether we survive and flourish or destroy ourselves, all of it takes on cosmic significance. Not because the universe cares. The interstellar medium is utterly indifferent to our existence, but because we care. Because we're the ones who can appreciate the cosmos, who can find meaning in its vastness, who can look up at the stars and wonder. Now, let's think about humanity's future. What happens if we do develop interstellar travel? What happens if we spread to other stars? Right now, we're a single planet species. Every human being who has ever lived, every civilization that has ever existed, has done so on this one small world. All our eggs are in one basket, and that basket is vulnerable. Asteroids have struck Earth before and will strike again. The dinosaurs were wiped out by an impact 66 million years ago. A similar impact today could end human civilization. Supervolcanic eruptions have devastated the planet in the past. The Toba eruption 74,000 years ago may have reduced the human population to just a few thousand individuals. Gamma-ray bursts from distant stellar explosions could sterilize large portions of the Earth's surface with little warning. And then there are the threats we create ourselves: nuclear war, engineered pandemics, runaway artificial intelligence, climate collapse. The obvious solution is to spread out. Establish human presence on the moon, on Mars, on the moons of Jupiter and Saturn. Build space habitats in the asteroid belt, and eventually reach for the stars. If humanity exists on multiple worlds around multiple stars, no single catastrophe could wipe us out completely. We would be genuinely resilient, genuinely long-lived as a species. But interstellar distances impose hard limits on what this spreading could look like. Any human colony around another star would be effectively isolated from Earth. The colonists couldn't participate in Earth's political debates in real time. They couldn't contribute to Earth's economy in any meaningful sense. They couldn't share in Earth's cultural developments as they happened. The communication delays we discussed earlier would make true coordination impossible. Instead, they would develop independently. Cut off from the home world, facing their own unique challenges, adapting to their own environment, they would inevitably diverge. Different dialects would emerge, then different languages, different customs, different traditions, different ways of organizing society. Over generations, the colonists would become a distinct culture, then a distinct civilization. Given enough time, they might become a distinct species. Humans on different worlds, subject to different environments and different selection pressures, would evolve in different directions. Over thousands of generations, the differences would accumulate. Humans who grew up in lower gravity might become taller and more slender. Humans exposed to different radiation environments might develop different pigmentation or different cancer resistance. Humans who lived underground on airless worlds might develop larger eyes and paler skin. Eventually, the populations might diverge so much that they could no longer interbreed, even if they somehow met. This isn't one galactic civilization spanning the stars. This is many civilizations, many cultures, perhaps eventually many species, all descended from the humans of Earth, but no longer connected in any practical sense. Isolated by the vast distances of interstellar space, each going its own way. Is this disturbing or beautiful? Perhaps it's both. There's something melancholy about the idea that humanity's children would be strangers to each other, that colonies founded with shared purpose would drift apart until they no longer recognized their common heritage. The dream of a united humanity spanning the stars seems noble, seems right somehow. The reality of fragmented, isolated outposts feels like a loss. But perhaps fragmentation is not a failure. Perhaps it's simply how intelligence works on cosmic scales. Perhaps the isolation imposed by interstellar distances is not a bug, but a feature. Diversity is strength. Multiple independent civilizations, each developing its own solutions to the challenges of existence, each exploring its own paths of cultural and technological evolution, might be more robust than a single, uniform galactic empire. If one branch fails, others survive. If one path leads to a dead end, others continue. The original human dispersal out of Africa, tens of thousands of years ago, led to exactly this kind of fragmentation. Isolated populations developed in Asia, in Europe, in Australia, in the Americas. They developed different languages, different cultures, different technologies, different adaptations to their local environments. For tens of thousands of years, they knew nothing of each other's existence. And then, eventually, they reconnected. Ships crossed the oceans. Populations that had been isolated for millennia met again. The results were often tragic, involving conquest, disease, and cultural destruction. But they were also generative, leading to exchange of ideas, technologies, and ways of thinking. The diversity that had developed in isolation became a resource for the reunited humanity. Perhaps something similar could happen among the stars, though on timescales of thousands or millions of years rather than tens of thousands. Perhaps civilizations that diverge will eventually find ways to reconnect, to share what they've learned, to benefit from their differences, or perhaps not. Perhaps the distances are simply too great, the isolation too complete. Perhaps humanity's children will never meet again once they leave the cradle of Earth. Either way, the galaxy is not and can never be a neighborhood. There will never be casual travel between stars, never quick visits to see how the colonies are doing. Interstellar distances impose a fundamental isolation that no technology we can imagine could overcome. Any future among the stars must reckon with this reality, or perhaps we never leave the solar system at all. Perhaps the challenges of interstellar travel are simply too great. Perhaps we spread through our own system, colonize Mars and the asteroids and the moons of the outer planets, but never make the leap to another star. Perhaps we remain a one-star species, forever, living and dying within a few light hours of the sun, never venturing into the great dark between stars. This wouldn't necessarily be a failure. Our solar system is vast. It contains enough resources to support human civilization for billions of years. We could build enormous space habitats, engineer worlds, create lives of abundance and wonder for trillions of people, all without ever leaving the sun's domain. Perhaps the interstellar void is meant to remain uncrossed. Perhaps it's simply beyond us, and that's okay. What does the scale of interstellar space teach us? What wisdom can we draw from contemplating these vast distances and empty expanses? The universe is vast beyond comprehension. We've spent hours tonight trying to build intuitions for interstellar distances, and still the numbers slip away from us. Light years don't connect to anything in human experience. Trillions of miles don't mean anything to brains that evolved to navigate African savannas. We can calculate with these numbers, reason about them, but we can't truly feel them. The universe is simply too large for human intuition. The void between stars is almost perfectly empty. Not just sparse by human standards, but empty to a degree that challenges the meaning of the word. Atoms separated by thousands of miles when scaled to human size. Vacuums tens of billions of times emptier than anything we can create. An environment of such profound nothingness that our concepts break down when confronting it. Most of the cosmos is cold, dark, and silent. The stars are islands of warmth and light in an ocean of frigidity and darkness. The universe simply exists, following its physical laws, evolving according to the mathematics of gravity and quantum mechanics and thermodynamics. There's no purpose written into the equations, no meaning embedded in the cosmic microwave background. And yet, here we are, on a small planet orbiting an ordinary star in an unremarkable corner of an average galaxy. Something remarkable has happened. Matter has organized itself into patterns that can contemplate their own existence. Atoms have arranged themselves into configurations that can wonder where they came from and where they're going. We exist. We're aware. We ask questions. We seek to understand. This is extraordinary. Not because it was intended, not because it was planned, but because it happened at all. Against all the cold indifference of the cosmos, against all the vastness and emptiness, here we are, warm and wondering. We care. That's what makes us remarkable. We look up at the night sky and wonder what's out there. We build telescopes to see farther, spacecraft to travel farther. We dream of reaching the stars even though we know how impossibly hard it would be. We tell stories about the cosmos, create myths and legends, populate the darkness with meaning even when the darkness has none of its own. This capacity for wonder, for curiosity, for caring about things beyond our immediate survival, this is what sets us apart. Not our size, which is insignificant. Not our power, which is negligible on cosmic scales. not our technology, which is primitive compared to what the universe allows. What makes us remarkable is that we wonder, that we reach, that we refuse to accept the darkness without at least trying to understand it. And there's something else worth considering. When you look up at the night sky, when you see the stars scattered across the darkness, you're not just looking, you're participating in something profound. The photons entering your eyes have traveled for years, decades, centuries to reach you. Light from Sirius has been traveling for nearly 9 years. Light from Vega has been traveling for 25 years. Light from Polaris has been traveling for over 4 centuries. Those photons have crossed interstellar space, traversed the vast emptiness we've been discussing, survived the journey through the void, and ended their voyage in your eyes. You're connected to those stars. Not in some mystical sense, but in a real physical sense. Photons that were generated in the nuclear furnaces of distant suns have traveled across light years of space to interact with the molecules in your retinas. Information about those stars, about their temperature and composition and motion, has been carried across the cosmic gulf and delivered to your brain. And it goes deeper than photons. The atoms in your body were forged in stars. The hydrogen was created in the Big Bang, but everything heavier, the carbon in your muscles, the oxygen you breathe, the iron in your blood, the calcium in your bones, all of it was created in stellar cores or supernova explosions billions of years ago. You are literally made of star stuff, assembled from atoms that were once inside other suns, atoms that have been circulating through the galaxy for eons before coming together to form you. You're part of the cosmos, not separate from it, not observing it from outside, but embedded in it, made of it, continuous with it. The same physical laws that govern your body govern the most distant galaxies. The same atoms that make up your flesh were forged in ancient stellar furnaces. We are not strangers to the cosmos. We are part of it, expressions of it. The universe become aware of itself. So what have we learned tonight? We've learned that the stars are impossibly far away. Light years of distance, tens of thousands of years of travel time with our best technology. Grains of sand separated by dozens of miles of emptiness. The interstellar gulf is real, and it's vast beyond human intuition. We've learned that the space between stars is almost perfectly empty. The interstellar medium, sparse and cold, with its phases and structures and hazards. Cosmic rays and dust and magnetic fields, threading through a void so empty that our concepts strain to describe it. An environment utterly indifferent to life, neither hostile nor friendly, simply vast and unconcerned. And we've learned that crossing this void would be extraordinarily difficult. Propulsion systems that might work, from solar sails to nuclear pulse drives to antimatter engines. Challenges of energy and mass and time. The isolation that interstellar distances impose. The communication delays that stretch conversations across generations or centuries. The fundamental constraints that physics places on any dreams of reaching the stars. And we've thought about what it all means. The Fermi paradox and the possibility that we're alone, or effectively alone, in the cosmos. The future of humanity among the stars. Fragmented and isolated if we spread. Vulnerable if we don't. The profound significance of our existence in a universe that exists without purpose or plan. Interstellar space is real. It's not just a setting for science fiction, not just a backdrop for adventure stories. It's the actual physical reality that lies between our sun and every other star. Cold, empty, dark, flooded with invisible radiation, almost impossible to traverse, a barrier that may forever limit what humanity can become, and yet beautiful, profound, humbling, a reminder of our smallness that somehow makes our existence more precious rather than less. We are tiny creatures on a tiny world, but we can comprehend the vastness, we can measure the distances, we can dream of crossing them even when the crossing seems impossible. The night sky is waiting for you. Go outside if you can on a clear, dark night. Look up. See the stars. Think about what lies between them. Think about the light years of emptiness, the sparse atoms drifting through darkness, the cosmic rays streaming past at nearly the speed of light. Think about the vast, cold, silent void that separates every point of light from every other. And then think about the fact that you're here to see it, that you exist, that after billions of years of cosmic evolution, matter has arranged itself into a form that can look up at the darkness and wonder, that can feel awe, that can ask questions and seek answers and dream of distant shores. The universe is vast, the void is empty, the distances are almost insurmountable, and we are here, small and brief and alive, looking up at it all with wonder. The stars are far away, but the light reaches us, and we reach back with our telescopes, our spacecraft, our questions, our dreams. We reach back because that's what we do. That's who we are. The creatures who wonder. The creatures who reach. Perhaps we'll cross the void someday. Perhaps we won't. Perhaps our descendants will walk on worlds orbiting other suns. Or perhaps humanity will live and die without ever leaving the solar system. We don't know. We can't know. The future is as vast and unknown as the interstellar medium itself. But we can wonder about it. We can think about it. We can feel the strange mix of loneliness and belonging that comes from contemplating our place in the cosmos. We can look up at the stars and know that we are part of something larger than ourselves. Something ancient and vast and continuing. That capacity for wonder is enough. It's more than enough. The void awaits. The stars are calling. And we are here, listening. Good night.